Hey, Tintin. Good morning, Jubila. Welcome back. Hi, Micaiah. Good morning. Hey, Irvin. Welcome back. Hi, Nadina. Hey, Michael. Good morning. Bellman. Wendy. Hey, Frank. Welcome. Good morning. Wait another minute. Please set your screen the way you want it to look. Hey, Philip. Good morning. Hello, Kim. Welcome back. All right, good morning and welcome back. Hopefully you guys are doing well. Hopefully you have a nice blanket of snow outside of your window. Hopefully you're enjoying the new weather that Central New York has to bring to us. Please check the attendance to the left. Please make sure Leonardo and Emma, please let me know if you're here. If I mismarked you. Either chat or mute. Okay. All right, so welcome on back. Let's just check out. All right, thank you. Let's just check out the COVID update, see where we're at so far. So COVID in Oneida County. Here's our snapshot of our graph of what's going on around us. So this is a full snapshot of the graph. COVID update. Really, we already went through the first part of the graph. Now you saw the first wave. Now, like the scientist said, the second wave's hitting, and it looks like it's hitting pretty hard. So let's just check out the snapshot of the second wave of where we are the last 10 days or so. COVID update for today. There's our bar graph. We have the y-axis. We have number of cases, positive cases on the y. X-axis, we have the dates. Hey, Emma, welcome. So you can see where we left off. Obviously, that big spike right there, huge one, 108. Now we're down to 90. Then we went down to 57 on the 15th. The 16th, we're at 64. Now looks like a uptick again. We're increasing again, 79. So again, we sound like a broken record, but all these people around here, all these cases, if you add them all together, all these people have COVID in our area. Be safe, be smart, protect yourself, protect your family, your loved ones. Wear a mask, social distance, wash your hands. Hopefully get a vaccine real soon. So that's our curve. Be smart. Let's move on forward. Get past this thing. All right, so welcome on back. Hopefully you guys are doing well. Welcome Wednesday. Our quote of the week comes from Thomas Edison. There is no substitute for hard work. Daily agenda for today, Wednesday, November 18th, 2020 to day one. We are continuing on with unit number 4, the periodic table. Topic number 2, the arrangement of the periodic table, we'll go through. We have some guided notes. We have a lot of YouTube flicks we'll analyze. A couple will analyze. Some of the other ones you can watch in your own time if you desire. I will put additional resources on there at times. And then you should be able to get through the exit pass. And I'll probably do a bunch of exit pass questions together with you as well. Yes, quarter one benchmark is the same thing as a 10-week exam. I do have yours, Kim. I did have you on the post earlier, but I do have yours, so you're all set on that. Hey, Leonardo, try to get here about 5 minutes earlier. No problem. So I do give you guys credit. It takes a lot of responsibility for you guys to stay at home and get engaged and try to work on this stuff. Logging into Zoom sessions. It's a big adjustment for you guys. My daughter's kindergarten. It's a lot of work just to kind of manage all that stuff. Am I on time? Am I there? If you don't have a schedule, set yourself up a schedule and put it by your refrigerator or something just to make a memory for yourself, or put a little timer in your cell phone and say, oh, I got this class, this class, this class. Doesn't hurt. So anyways, we need a reference table. We need our guided notes, and we also need some videos here. So I attach those there as well. All right, no problem, Leonardo. I hear you. Got to take care of mom. So we have all this information we're going to do. We'll watch a few of those videos. If you ever want to watch or jump ahead, I have the guided notes key there for you. Maybe you want to do that the night before and then just kind of like listen and kind of observe or just take in what's going on in class as well. It's up to you on that, what you want to do. So please open up your guided notes. We left off on the history of the periodic table we went through. We talked about the Russian chemist, Dmitry Mendeleev, his nice guy. His periodic table is arranged by increasing atomic mass. The problem with his periodic table is there's gaps in the periodic table, or the masses were out of order. Then we stopped to England, and we talked about Henry Moseley, how he arranged his periodic table by increasing atomic number or the proton number. His periodic table was more organized. It increased by atomic number. He also developed and discovered the proton. This is how the modern periodic table of elements is arranged. We talked about the periodic law, how groups or columns, as you go down a group, you add another principal energy level. We talked about as you're in a row, you add a proton number and one more valence electron. We talked about at the end of every row, the valence electrons equals 8. Start of row is equal to 1. The valence electron tells you how many bonds it could potentially bond with as well. And we talked about elements in the same group have similar chemical properties. Why? Because the number of valence electrons are the same. Elements in the same group have similar chemical properties. We talked about periods, the horizontal periods, horizontal rows. There are 7 periods in the periodic table of elements. We analyze several elements in one period, period number 4. And we saw that there's 4 rings for each of these, but the number of valence electrons varied throughout a period. So again, a little refresher from last time. What do? We went through several examples here. We analyzed elements of a specific period, period number 4. So we went through several elements of this period, and we noticed that all the elements in that period had the same number of rings, but the valence electrons differ. So every element in the period has that number of rings, whatever the period is. Every element in period 4 has 4 rings. The only difference is the number of valence electrons and maybe the total number of electrons as well. So the number of valence electrons varies and changes. We should definitely know that every element in group number 1 has 1 valence electron. Every element in group 1 has 1 valence electron. Every element in group number 2 has 2 valence electrons. We should know that transition metals, they're a little funky there. So transition metals, they do not follow that sequence of number of valence electrons. But if we analyze the other half of the reference table, I should have just zoomed in on this one. Group 13 has 3 valence electrons. 14 has 4 valence electrons. You should be able to see that. 15 has 5 valence electrons. 16 has 6, 17 has 7, 18 has 8 valence electrons. Those are common traits that you should just automatically be aware of. You should know how many valence electrons are in each element. If I say, hey, check out an element in group number 16, check out SE. It's in group number 16. How many valence electrons does it have? You should automatically say, oh, it's in group 16. It has 6 valence electrons. So you should be able to look at it that way and say, every element in this group has 1. This one has 2. This one has 3, 4, 5, 6, 7, and 8 valence electrons. If not, we're going to get closer and closer to knowing that stuff more and more each and every day. All right, so we analyze the periods. Today we're going to analyze the groups of the periodic table. The groups of the periodic table are going to be the vertical columns, up and down columns. So vertical columns. I'm going to cap lock my keyboard, and then I can just put my information right in there without changing the font color or size. Vertical column, they run up and down in the periodic table of elements. So vertical column check out the periodic table again. Periodic table of elements, hopefully you have a hard copy in front of you. On the periodic table of elements, there are 18 groups on this periodic table. So you can see the groups here. There are 18 groups on the periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13 through 18. They're the up and down columns. Group 1, 2, so on and so forth. The main group of elements, there are only 8 main groups on the periodic table of elements. They exclude the transition metals. So the main groups would be, this would be main group 1, main group 2, this would be the main group 3, 4, 5, 6, 7, 8. So it's funky. There's 18 groups on the periodic table of elements, but there are 18, there's 18 groups in the periodic table of elements, but there's 8 main groups on the table. So that's what the image kind of outlines there. 28th is Thanksgiving, Santino. I'm hungry too. They're making me really hungry. But that Tuesday, Wednesday, Thursday, no, we're in school on Tuesday, but Wednesday, Thursday, and Friday we have off. Yeah, Monday, Tuesday, then we're off. That perfect. Thank you. Okay, I'm all over the board. So let's go. All right, use the periodic table, chemistry reference table. Complete the table below for group 1 elements. So analyzing just group 1 elements here. We're going to do the same thing we did last time. I'll do a first few, then we're going to go through and have you guys help me out as well. So the first element is going to be H. Check out H on the reference table. Go to the next page. You can figure out the name of H. Hopefully you know H is going to be hydrogen. So I'm going to copy hydrogen on in there. So that's definitely hydrogen. The electron configuration for hydrogen is just going to be 1. So electron configuration is the bottom left-hand corner. Some people in my other class still don't know where that is. It's the bottom left-hand corner. It is going to be 1. That also has one valence electron. So there's only one valence electron hanging out, chilling in the last row, last shell. To make this Lewis dot diagram for H, I'll make this one nice, and then I'll just edit them and copy and paste them for the following. Click on the Lewis diagram, go to Insert, Drawing, New, make a text box, T, put a H there, which is my kernel. It represents the protons, it represents the neutrons, and the non-valence electrons. So that symbol for Lewis dot diagram represents protons, neutrons, and the non-valence electrons. Around the kernel is going to be just one dot, one of the shapes, and I'm going to make a smiley face because my smiley faces are my electrons. Small little sneaky little electron. I don't care if you make it a dot, but I told you I'm going to stay consistent. My electrons are going to be just a smiley face. So I don't care which way you represent it. Maybe you just want it to be a simple dot, which is totally fine. It's accurate. If you put a little electron with a smiley face on the regents, you'll get the point, but it could just be a dot instead. So if you just want it to be a dot, that's totally fine. That's what it should be. But add a little joy. Once you have that image, save it and close it. If at any time I go too quick, please throw it in the chat or unmute yourself, and I will slow down and do it again for a second time or maybe a third time. But a lot of this stuff, I think after practice, we're getting the hang of it, how to do some of this stuff. Next element is going to be the second one down on that group. It's going to be Li. The name of Li, go to the next page, the reference table, is going to be lithium. Lithium. The electron configuration for lithium, scroll on back, is going to be, it's in period number 2, is 2-1. 2-1. Valence electrons, if I look at the last number of electrons, the last ring, it tells you how many valence electrons are present. There's only one valence electron present in that one. The Lewis dot diagram for lithium, what I'm going to do, I'm going to click on the image I just created. I'm going to hit Control C, I'm going to copy it, and then I'm going to paste it below by hitting Control V. So it's pretty darn close. We have one valence electron, one smiley face. We're going to go there. If I double click it, I can switch my symbol to Li. So double click on the image, double click on the H, and just put Li. That's my Lewis dot diagram for lithium. Save it, close it, good to go. All right, I'm just going the order of my class from start to the bottom of participants. I'm going to go through the questions, and please try to tell me your best answer for the following. Alan, you're the first one up on this. Na, what does the symbol Na represent? Which element?
Sodium.
Sodium. So you can find on this page, there's sodium. This is my electron configuration.
2-8-1.
2-8-1. 2-8-1. How many valence electrons?
There's one.
1. Thanks, Alan. So there's my electron configuration, 2-8-1, really easy. You found that stuff pretty quick. Hopefully you could too. I'm copying and pasting my lithium. So my image has got the blue box around it. Copy, Control C. I'll paste it below, Control V. Double click on the image and switch out the symbols. Li to Na. Not available anymore. It has one valence electron. It's not available. Sorry, guys. Girls, whatever. Next up on my list, C, here we go. Okay. You have K. What's the symbol K represent?
Potassium.
Potassium. All right, potassium configuration, please, when you're ready.
2-8-5.
What's the last number?
5.
Where'd you get 5 from? 285, 28.
From the electron configuration.
So K, you have K here. This
Okay,
28.
I was looking at P.
Okay, gotcha. Yeah, that's a little tricky. But that's not tricky.
It would be
2881.
2 dash.
You
Yeah,
see it, right? All right. So 2881. How many valence electrons?
1.
One valence electron. Thank you. All right. So yeah, K is potassium. That one is tricky. Sometimes the symbols don't correlate to the English words. All right. So one valence electron. Again, what I'm going to do, I'm going to copy, paste, and edit. So copy, Control C, paste, Control V. Double click the image. Double click the text. Change NA to K. Save and close. Am I going too fast for anybody? If you're nervous, you don't want to say anything, then you could rewatch the video. You have the ability to do that. But you could feel free to ask questions if you need to see something again. Next up on my list is Bellman. Bellman, what's RB represent? Which element?
Rubidium.
Rubidium. Find element number 37. Next page. Rubidium. Element 37. Element 37. There it is. Rubidium.
Its electron configuration is 2, 8, 18, 18, 8, 1.
I have too many 18s. All right. So it's rubidium. Electron configuration 2, 8, 18, 8, 1. Yeah. Too many 18s. Thank you. I think you said it right. Just got excited here. So rubidium's location's in period number 5. We should know I should have 5 rings. 1, 2, 3, 4, 5. It does have 5 rings. We have 1 valence electron. Thank you very much, Bellman. 5 rings, good to go. 1 valence electron. To make my Lewis dot diagram, click the image, copy, Control C, paste it below, switch the symbols on out. Click RB. Save it, close it, on to the next. FR, Emma, please type in the chat or unmute yourself. What does this symbol FR stand for? Element 87. So FR stands for what element name? This is the atomic number. Match it on up. Find the atomic number 87, and 87 is going to be francium. Francium, this is the origin where it was discovered. It was discovered obviously in France. Electron configuration, please. So what's the electron configuration for francium? Find FR in the reference table. There it is. It's my electron configuration. You have a tricky one here, actually. So francium. Hopefully you can hear me, Emma. All right, so francium's location is element number 87. It's located at period number 7. So this has to be a part of the electron configuration. Just going to copy and paste that in. But if I look at that, there's only 1 ring, 2, 3, 4, 5. It's missing some of the rings there in that situation. So some of the rings are missing. If I scroll down the reference table a little bit more, you can see there's some key information there. It denotes the presence of 2-8 for elements above 72. Any elements above 72 are missing the first 2 rings. So that asterisk there tells you you need to put 2-8 for elements greater than 72. All these elements, they need 2-8. You're missing the first 2 rings. Same thing for francium. You're missing the 2-8. So it must be 2-8 out in front. If we put the 2-8 in front, we now have 7 rings. Another thing to note is if you look at this element, this tells you the maximum number of electrons you can have in the first 4 rings. First ring has maximum of 2 electrons. Second ring has maximum of 8. Third one has maximum of 18. And the fourth one has a maximum of 32. Those are good to know as well. 2, 8, 18, 32. That's the maximum number of electrons you can have for each ring, at least the first 4 rings. And the Lewis dot diagram, if I copy and paste that image, Control C, Control V, whoops, copy that image. Now we could just edit this to make it into francium. It has 1 valence electron. So double click on the image. You can switch that to FR francium. Easy. Save it, close it. Good with that portion of groups analysis. So what did we just do there is we went through elements in group 1 of the periodic table. We analyzed elements in group 1, and we analyzed the Lewis dot diagrams that associated with it. So we went through all these elements here. We noticed that every element in group 1 had 1 valence electron. Yeah, I did forget to put cesium on there, but that would have been true to it as well. So every element in the group has 1 valence electron. That's why they have similar chemical properties. All right, moving on forward. Next page. Practice questions. I'll wait for one correct answer, and then we'll move on forward. Mendeleev arranged his original periodic table according to what? What was the problem with this periodic table? Please put it in the chat. Dmitry Mendeleev arranged his periodic table according to atomic mass, yep. And there were gaps in this periodic table. The problem is that there were gaps in the table, or the mass wasn't always increasing. There were gaps in the table. Question number 2, Henry Moseley, the English chemist, he proved the existence of what subatomic particle, and how did he arrange his periodic table of elements? So Moseley's periodic table was arranged, or what did he discover first, and then how was it arranged? The first thing subatomic particle discovered was proton. And his table is arranged by increasing atomic number. Good. Or increasing proton number. Same thing. You know that now. Proton number, atomic number, same thing. How many electrons does the last element in every, no problem, Emma. No, how many elements does the last element in every row or period have in its valence shell? What's the last element in every row? Check it on out. So the last element in every row. Here's a row. So let's just analyze one row here. Okay. The last element, the valence shell. Last element in every row. So here's one row, and we're just going to focus in on the last one. For example, last element of every row, that right there. I want to know how many electrons are in that last row. How many valence electrons are in the last row? H is the number. So there's 8 valence electrons. How many electrons does the last element in every row have in its valence shell? 8 valence electrons. Okay, next up, that should have been 8. Number 4, what happens to the energy levels as you move across a period? As you move across a period, what happens to the energy levels? Across a period, what happens to the rings? Yes, Tintin. Yes, Jumila, thank you. They remain the same. They're not changing. Every element period number 5 has 5 rings. You don't change the number of rings you have. So they remain the same. Remains the same. Remains remains the same. What happens to the number of energy levels as you move down a group? So as you're going down a group, yellow and timber, so you go down a group, what happens to the energy levels? Going down a group, the number of rings, they increase. Several right answers there. Thank you. So number of rings increases. Chemical properties of an element are based on what? Chemical properties of an element are based on their chemical properties of an element are based on their valence electrons. Good. So elements in the same group have the same number of valence electrons. Therefore, they're going to have similar chemical properties because they're going to bond with similar groups. So valence electrons. Periods of a periodic table are similar to what in a calendar? Periods are similar to what in a calendar? Yeah, periods are similar. So periods, this would be like a period, this would be period, period. There's 4 weeks in a month. This would be like a period. So weeks would be similar to period. Groups are similar to what on a calendar? Groups. What's going to be a group on a calendar? Yeah, definitely the days. Days of the week. 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 Sunday and there's Monday. There's Tuesday and there's Wednesday. There's Thursday and the Friday. These are the days of the week. Sorry, my daughter's in kindergarten. Just thinking about these things all the time. I hope I know the days of the week. Hopefully you do too. If you need help, I'll sing it to you. It's on this recording. You can listen to it again. All right, number 9. Use the calendar analogy to explain whether it's more likely to find similar characteristics among the same groups or elements of the same period. Where are you more likely to have similar characteristics? Groups or periods? Or days or weeks? They're never going to ask you a question like this in the Regents. Wow. Calendar analogy. In a calendar, what's going to be more similar? Days or periods? Days or weeks? In this situation, days are going to have more similar characteristics. You're going through the week. If it's Sunday, you're starting to get excited because you have chemistry class the next day. When it's Monday, you're like at high, you feel really good about school, you're motivated. Then you get to Tuesday, Wednesday, Thursday, Friday. Friday, you're like all bummed out, like, oh, great, the weekend's coming up, and I'm not gonna see Mr. Brown for a couple of days. So then you like start to be bummed out. I feel this way, hopefully too as well. So you feel a certain way on Monday or Tuesday. Wednesday's hump day, so you're like, oh, halfway there for the week. But then Friday you might be motivated, excited. So similar characteristics would be among days or groups. I don't know. I'm not just going to be like that. Okay, number 10. What happens to the number of valence electrons as you move across a period? Number of valence electrons as you move across a period. Yeah, they increase by 1. No problem. Valence electrons as you move across a period are going to increase. Valence electrons as you move across a period, just check them on out. Across a period, what happens to the number of valence electrons? It goes from 1, 2. Don't worry about this transition group here in the middle. That's in Proctor Pride there. That's not part of the main group, but this would be 3. It's increasing, increase, increase. Yeah, they're definitely increasing as you go across a group. So definitely increase. Increases. What happens to the number of valence electrons as you move down a group? Going down a group, what happens? Going down a group, we just analyzed this in class. So as you go down a group, what happens? They remain the same. So main group elements, as you go down a group, there's 2 valence electrons, 2 valence electrons, 2, 2, 2, 2. 2 valence electrons, they remain the same. Remains the same. And last question, use a concept. Valence electrons to explain whether it's more likely to find similar characteristics among elements in the same group or elements within the same period. Where are you more likely to find similar characteristics in a group or a period? Same group, because they have the same number of valence electrons. Same group because they have the same number of valence electrons. A lot of this stuff we already know. Some of it might be newer to you, but most of it we are aware of one way or another. Okay, that takes care of that topic. On to topic number 3, or the arrangement of the periodic table. It should be topic number 2. It's a continuation of it. Now we're on to the groups of the periodic table. This portion of the periodic table we already went through. We already went through majority of this. We figured out the groups. You did this on a crash course day where I went through it really, really quickly. Again, I'm not going to grade that crash course guided notes from the day before the benchmark. I wanted to cover it in the event that some questions were on there. I rushed through it. I know I hated that I rushed through it, but you had the ability to answer questions because you did see it. But now we're going to take it a little bit slower as we go through this process. So this is similar to that version we did on Thursday, last Thursday. This one, though, I will be collecting. I'll be grading it as well. The crash course, that second half of that Thursday class, I'm not going to go through it. I'm not going to. You could turn in. I'm not going to check it. I'm not grading it. Whatever. All right, so here we go. The first group of the periodic table we're going to analyze, just like we did the other day, is going to be the. Hi, Jumila. Oh, I saw Jumila. How you doing, Jumila? Oh, first time I've ever seen a student. I just see blacked out screens here. That's cool. That's cool. I have 2 computers here. So I have my desktop in front of me, and then behind me I have you guys like blacked out screens with your name there. So I was excited there. Hi, Jumila. No, that's all right. Maybe your camera's on all the time, but I just saw her for a second, so that made my day. Thank you. But back to this. I should do a flashlight again. Maybe not. Alkali metals are part of a family, just like you and your siblings in your family. All alkali metals are part of the same family. They have the same last name. So maybe they have the same parents, maybe they have the same mother, but they have the same last name. They have similar chemical characteristics, just like you and your siblings. You have similar characteristics to each other. Maybe the same skin tone, maybe the same hair color, eye color, whatever it may be. They all have 1 valence electron. They can easily lose their 1 electron to become and form a positive 1 charge. So once they lose 1 electron, they become a positive 1 charge. They are extremely reactive. They react very easily. They're never found alone in nature. They contain the most reactive metal, and it's probably going to be the lowest one on the bottom, francium. But it's so rare. We go with cesium as the most reactive element. We say cesium's the most reactive element because we can't even get our hands on francium to see how reactive it is. So cesium, we're saying, is the most reactive element. This first video I'm going to play is going to be analyzing these elements when you mix them with water. You'll see that the reactivity increases as you go down the group by obviously the reactions that's there. But on the other hand, I do have to warn you, I apologize in advance. There is some foul language, but you guys are in the 10th, 11th, 7th grade. So hopefully you guys can be mature enough and ignore it. But it is a good video, so I want to play it anyways.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. OK, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
OK, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
All right, hopefully you enjoyed that video. Obviously, you can see what happened in that situation. You added an alkali metal with water, and there's a small reaction. Then it got a little bit bigger with sodium. Potassium was bigger. Rubidium was even larger. So obviously, as you increase, or when increase in the atomic number, basically, the reactions increase as well. So again, I apologize about the language, and I hope you enjoyed the HD quality on that one as well. It's really good quality. So what's going on here? We have a nucleus, and we also have, so for lithium, we have a nucleus, and then we have 2 rings on lithium. It's in period number 2. Francium still has a nucleus, but this one, it doesn't have 2 rings. It has 7 rings. So obviously you can see this and you can say, oh, there's 2 electrons there, there's 8 there, 18. That's ring number 3, ring number 4, 5, 6, oof, 7. But obviously you can see the numbers of rings, it increases. This francium is definitely larger than the lithium. So I like to think about this way. Why does it have more energy? Why is it more reactive? Because if lithium has 2 rings, I think the rings as cheeseburgers. Maybe Santino wants to think of them as turkey dinners, whatever, Thanksgiving. So this lithium has 2 rings. It has 2 cheeseburgers. And francium has 7 rings. It has 7 cheeseburgers. If lithium eats 2 cheeseburgers in 1 week versus francium, which eats 7 cheeseburgers in 1 week, francium is going to have more energy. It's a little bit bigger. The more you eat, the bigger you have, the more energy you could have to burn off. So francium has more energy. It's bigger. Therefore, it's more reactive. Lithium only had 2 cheeseburgers. It's not really, doesn't have a lot of energy in them. It can't give off much energy either. The more energy you have, the more energy you could give off in the situation too. So that is alkali metals. Next up, group number 2 are called alkaline earth metals, the earth metals. They all have 2 valence electrons. They prefer to lose their 2 valence electrons and become a charge of +2. They are the second most reactive. They're fairly reactive. Second most reactive group of metals. They're never found alone in nature. So if you're trying to check out in the streets, walking the Genesee Street looking for some beryllium just chilling on the ground, or magnesium by itself on the ground, or calcium, you're not going to find it by itself. If you're mining for these things, they're not going to be by themselves. They may be together, but never alone. Let's watch a flick on alkaline earth metals. I'm not gonna play this whole video. I'll play a portion of it, but not the entire thing.
In this lesson, we will learn about the alkaline earth metals in Group 2 of the periodic table. We will focus on magnesium and calcium and learn about how they react with oxygen and water and the products formed from these reactions. The alkaline earth metals are beryllium, magnesium, calcium, strontium, barium, and radium, located in Group 2 of the periodic table. These metals all have 2 electrons in their valence shell, and with the exception of beryllium, can lose these valence electrons to form an ion with a +2 charge. Like the alkali metals, these metals, except for magnesium, are stored in oil. Similar properties and reactivity trends are also observed. Moving down the group, their density and reactivity increases. Melting points and boiling points decrease, and the metals become softer. We will now learn about the reactions of magnesium and calcium with oxygen and water. Magnesium is shiny and silver, but you will see that your magnesium strip may be dull. This is due to the formation of an oxide layer from exposure to air. Simply clean it with steel wool, so to remove as much of the oxide layer as possible. Using a pair of tongs, take the magnesium strip and hold it to a roaring Bunsen burner flame. The combustion of magnesium proceeds with a bright white flash. Take care not to look at this flash. Magnesium reacts with oxygen to produce magnesium oxide, which is a white solid. Here is a challenge. Do you expect calcium to be softer or harder than magnesium? Please pause the lesson to think about this and resume when you are ready. Calcium is softer than magnesium. Moving down the group, the metals become softer. Overall, though, these metals are harder than the alkali metals. Calcium is also shiny and silver. Using a pair of tweezers, take out a chunk and cut a small piece using a scalpel. Remove excess oil using paper towels. Using tongs, place in a roaring Bunsen burner flame. You will observe that it burns with a red flame. Calcium reacts with oxygen to produce calcium oxide, which is a white solid. So magnesium and calcium react with oxygen to form their respective oxides. Let the formed calcium oxide cool. It's important that you allow it to cool sufficiently because the next step is exothermic. Place the cooled calcium oxide in cold water. Calcium oxide reacts with water to produce a solution of calcium hydroxide.
Okay. I'm going to stop that video there. I do want to check back at 2 minutes of the video. 2 minutes into the video, they took something here. So I do want to analyze this as well. So 2 minutes into the video, I know you can't really see this too well. There's magnesium plus oxygen yields magnesium oxide. So we'll get into this stuff soon. We'll figure out the dynamics of this as well. So Mg plus oxygen yields magnesium oxide. Hold on to that thought. We're going to do a little demonstration on this. So when I, get rid of that for a second. So when I take some magnesium, just a piece of magnesium strip here. So there's some magnesium. It's a soft metal. It's very malleable. You can bend it pretty easily. It's a thin little sheet. It's called magnesium ribbon. Nice little shine to it. What I'm going to do is I'm going to take some tongs, some nice safety goggles, take some tongs, and I'm going to make this lit. I'm going to light it up. So I'm going to take this, my tongs, my magnesium ribbon. I'm going to sight these electrons because got to make it a little bit more exciting around here. It's pretty boring in this classroom, no one here and just hanging out. But anyways, I'm going to take my butane lighter. I'm going to light this up and I'm going to excite those electrons. What's going to happen is going to give off a bright light in the situation. So when I excite those electrons, I'm going to turn off the side a little bit. Shouldn't look directly in it, but you guys are not live in front of it. You're just going to see a bright color on your screen. But you can see what exactly is going on there. When I excite magnesium, it's pretty reactive. It didn't take much heat to burn this metal in this situation. And when I burn it, it gives off that bright color light. So that is a pretty reactive metal for magnesium. That is magnesium ribbon and me exciting it as well. So that was that reaction that we just saw on the image as well. So that right there, we took magnesium, we took some oxygen, excited them, and it made some small magnesium, which is on the bottom. It's like a little dust on the bottom. Magnesium oxide on the product side. All right, so that's alkaline earth metals. Hopefully you guys can still see. Alkaline earth metals, fairly reactive. Let's jump on down to the transition metals. Transition metals, the main group elements does not include the transition metals. In the transition metals, they're found in the middle of the periodic table. It's called the D block. Maybe we want that for the future. They formed colored ions. So when you excite them, they give off a specific color. So like that red, the green. When I excite those electrons for the flame test, you saw this. It gave off different colors there. That greenish color, bright blue color, was copper when I excited the electrons. This concept is typically going to be on the regions. So transition metals is always on the colored ions are always on the regions. I don't know if we're going to have regions. I'm going to do my job. Hopefully you do your job as well. I'm going to prepare you to the best of my ability, virtually, to prep you for that regions. You never know what's going to happen. You never know if you want to be an awesome chemistry teacher like the one you had in high school. Maybe you do, you know? Maybe you want to get to engineering when you're 20. You might need this chemistry stuff to help you out as a backbone. You may not think you're going to take or college chem in college, but most of you guys, if you're going to medical, nurse, doctor, engineering, any science field, you're going to need it. So hopefully take this on to the next level. They're going to expect you to know it regardless if we had a pandemic or what. So just do your part. I'll do my part. I hope I haven't let you down yet. These tend to be the unpredictable elements. They're not predictable for their valence electrons. Unpredictable. Almost every transition metal can form a different number of bonds. Depending on what other elements the polyatomic elements or polyatomic ion are present. They have multiple oxidation states. That's why the oxidation numbers are different for all of them. The valence electrons are going to be different, but they're all going to be like a positive. They all like to lose one valence electrons. This is the least reactive group of metals. That's why we use them for making jewelry, making buildings, making bridges, making cars. Iron's in there, nickel, cobalt, copper, silver, gold. All those things are in there because they're not reactive. They're using aluminum on Ford F-150 trucks because they're not reacting with the salt as easily as maybe the iron did. Each metal is going to be a different reactivity rate. Most likely to be found uncombined in nature. So these guys, if you do walk or go snowshoeing later today down or up on Valley View, Valvallis ski resort in Utica on the Parkway, if you're looking for these elements, you have a chance to find them if you start mining for them. If you dig, you'll find some of these, maybe some iron. Hopefully hit some gold. Next group of elements is going to be BCNO group. This is the miscellaneous group of the periodic table. There's not a specific name. This is just a random group right here. Miscellaneous group. This contains metals, nonmetals, and metalloids on the periodic table. So the miscellaneous group, they're not going to ask you any questions in the reasons on this one. But this miscellaneous group, I'll go back to that. So this group right here is referring to BCNO. B would be group number 13, C is group number 14, N is 15, and O. So this group has different properties within it. You have metals, you have nonmetals, you have metalloids all within it. There's not a specific name for that group. We will specifically talk about carbon for a whole unit and the bonding of carbon. So that one's important. I'm not saying they're not important, but it's not a specific group for that one. Not a specific name of these groups. It's not a family. So miscellaneous group, they're metals, nonmetals, and metalloids. Quick little review here on this metalloids. We have the metalloid staircase. That staircase is outlined. Here's my staircase. It divides my metals and my nonmetals. Metals are to the left, nonmetals are to the right. So this is my dividing point for my metals and nonmetals. All metals are going to be to the left. So on the staircase, everything to the left are going to be metals. Everything to the right are going to be nonmetals. But we have metalloids, which are in the middle, which divide the metals and nonmetals. There's 7 metalloids. They are on the staircase. The first one's B. The second one's on the staircase. It's SI. Third one's on the staircase. It's AS. And TE is on the staircase as well. They're on the staircase. There's my staircase. They're on top. The next one's going to be straight down, and they're going to follow their way up. PO, SB, and GE. There are 7 metalloids. Metalloids have properties that are similar to metals and similar to nonmetals, depending on their pressure and their temperature. AL, aluminum foil, think about it. That's a metal. It's a solid. It's malleable. It's a good conductor of heat and electricity. That is not a metalloid. 7 metalloids. B, SI, AS, TE, PO, SB, GE. You should be aware of where the 7 metalloids are. The staircase divides metals and nonmetals. All right. Next up is halogens. So halogens are group number 17, very popular nonmetal group that bonds. Group number 17. Halogens have 7 valence electrons. They like to gain 1 valence electron. When they gain another electron, if I gain another electron there, it becomes a -1 charge. And remember, stable octet, or 8 is great, whatever way you want to think about it. It needs 8 valence electrons. That corny phrase. When they gain electrons, so when Cl gains an electron, it gets it probably from group 1. This would form salts or a compound, which is called a halide. Halides are halogens. So when Na and Cl bond together, Cl is in group number 17. You can see it over there. So when Na and Cl bond together, Cl has 7 valence electrons. Na has 1 valence electron. When this bonding happens, Na is going to transfer a bond or electron over there. It's going to migrate, it's going to move. Na loses that 1 electron. So it lost that 1 electron. If it loses that electron, it now becomes a +1 charge. For positive ions, you need brackets around it. This gained the electron, you need brackets around it. Since it gained 1 valence electron, it becomes a -1 charge. And now that is going to be a stable octet. So when Na and Cl bond together to make table salt or sodium chloride, this guy loses, this guy gains the electrons, and that's called a halide. Halides, salts, halides, they're referring to the same type of thing. This contains the most reactive nonmetals. Most reactive nonmetals, and the most reactive is going to be the first one on top. So this one's a little bit different. Which one gains electrons easiest? It's going to be fluorine. Fluorine gains electrons easiest. All phases of matter make up this group. And you have solid, liquid, and gases. So gases, liquids, and solids in this group. Only group in the periodic table has all 3 phases of matter. An example from this group could be chlorine. Check out all 3 phases of matter of that group. So group 17 has all 3 phases of matter. You should definitely know the phases of matter of the periodic table. We'll have another topic on this as well. We'll talk about 3 phases. I'll go back to that in a second. So it's really easy to know the phase of matter. Which element's a solid, which one's a liquid, which one's a gas. So right from the get-go, I told you to memorize the 2 liquids on the periodic table. There are only 2 liquids on the periodic table. It's not that hard to memorize 2 elements. 2 liquids on the periodic table. One of them is my element. Hi, I'm Mr. Brown. Mr. Brown, Br is bromine, that's a liquid. And the other one is mercury, the stuff they used to use in thermometers when your grandparents were around or alive. Maybe great grandparents, I don't know, depends on how old they are. All right, so mercury and bromine are the 2 liquids on the periodic table. The gases are going to be hydrogen and helium. And then the other gases are going to form a 7 to the right of the nonmetal. So it starts with nitrogen, it goes all the way over to neon, to the noble gases. And then this number 7 is the noble gases as well. So these noble gases are gases. Hopefully you can see that there. I just made a 7 there. So that 7, you can see that big 7. You have hydrogen, you have helium, and the last one's going to be chlorine. All the red there are my gases. everything else is going to be a solid at STP. So reds are gases, hydrogen, helium, gas. That big 7 starting from nitrogen all the way on over to noble gases. Chlorine is a gas. The 2 liquids are bromine and mercury. Everything else is solid. So that's an image you should definitely understand and hopefully memorize that. You should know the phases, gases, 2 liquids, everything else is solid. So you can definitely tell most elements are going to be solids at STP. All right, next group is noble gases. The noble gases of the periodic table, they are unreactive elements. Noble gases, group 18. Unreactive or inert. This is a family as well. They have very similar properties. They have 8 valence electrons, or stable octet. They have a stable octet, which have 8 electrons. 8 electrons in their valence shell. Octet. This group is the most stable group. Most stable group on the periodic table. They exist alone in nature. They do not want to bond with anybody else. Group fine being completely by themselves. You will not see any chemical bonding in this course with anything in the noble gases group. They're fine being all by themselves. They're all stable octet, exception of one of these elements. The exception is going to be helium. And within helium, exception to the octet, the exception to the stable octet, sorry guys, it just got logged off for some reason, kicked me out for a second, I don't know. Exception to the octet is going to be helium, which only has 2 valence electrons. Everyone wants to be a noble gas and have 8 electrons. 8 is the number, 8 is great. Example could be neon from this group, and E. Couple more different portions. Hydrogen, not officially part of group. H is like all by itself over to the left of the periodic table, just hanging out. It looks like it's in group 1. It is both a nonmetal and a gas at STP. So this guy right here is in group 1. Yeah, it's definitely gonna be in group 1 because it has 1 valence electron, but it's not part of the alkali metals because it's not a metal. It's not a solid STP. It's a nonmetal. So that guy's a nonmetal. So this is the only element to the left of the staircase that is going to be a nonmetal. It can be represented for H as H2 to make that subscript 2 control comma 2. It could be represented as H plus control period, makes you raise that on up, or it could be represented as H negative. I'm not concerned if you have super and subscripts there. That's not a big deal. But you will see how it's going to be represented with each one of these throughout the duration of the year. All right, the last thing that you really don't know too much about is lanthanides and actinides series. We should know and be aware of that lanthanides and actinides actually belong to group number 6 and group number 7. They should be inserted there. But the problem is if we did insert that portion, obviously on this periodic table, what would happen is if we had a periodic table with the lanthanides and actinides series there, it would look quite a bit different. So you would have group 1 and group 2. You would have the lanthanide series, which would be like extremely long. Then you'd have the transition elements, which would be there as well. And then you'd also have nominals all the way to the right. So the periodic table of elements, I know is a poor choice of color at the end, but the lanthanides and actinides series, that's what would happen to the periodic table of elements. It would look quite a bit different. So again, this is group 1, group 2. This would be the lanthanides and actinides. And then all the way to the right, we have the transition metals. And then this would be the BNOC group. Then you'd have halogens and noble gases there as well. There's my H, that's still be there, and helium still be there. The problem is with that, if we insert the lanthanides and actinides in there, each one of these elemental boxes would be like really small to analyze. And think about the piece of paper we need to really satisfy each of these elements. It'd be a lot smaller to interpret. So the reason why we don't have the lanthanides and actinides series there is just because it's going to take up a lot more paper and it'd be tough to really interpret and analyze these elements. They actually belong to group period number 6 and period number 7. And that's it for notes today. They belong to period 6 and 7. A lot of these elements are man-made elements, especially 89 and greater from the actinide series. We will analyze uranium. We'll talk about nuclear chemistry. We'll talk about uranium there. A lot of these elements over here too are going to be man-made elements. All right, so that's it for notes. The last thing for today's class, I'm just going to do a couple questions from the exit pass, and that's going to be it for today. You could watch the additional videos if you want. I'm not going to watch the rest of them. You could watch them if you want. So after the other notes, I'm going back to my home screen, going back to my stream, and I'm going to do a few questions from topic 1 and a few questions from topic number 2. So exit pass, topic number 1. This should be the history of the periodic table. It's the same one. I made a mistake there. So topic 1, the arrangement of the periodic table, and do that. I'm going to click on that. I'll do maybe 4 questions from this topic and 4 questions from topic number 2. All right.
We did that one, topic 1.
We did a
last
bunch of questions already?
We did 5 questions last
Okay,
class.
forget it. Let's just do topic number 2 then. You can do the rest of topic number 1. Did we do topic 2?
No.
All right, let's check out some from topic 2. Good. No one did it, so that's even better situation. All right, please put your best answer here. Probably want a reference table handy as we do it. Beryllium is classified as what? I'll wait for 5 correct answers, then I'll discuss it and I'll give you the right answer. Beryllium is classified as what? There's BE, beryllium. Thanks, Kai. Yep, 1. Thanks, Alex. Good to go. 2. Beryllium's classified as what? Oh, Santino, check out my turkey behind me. How my turkey looks, Santino? Huh?
What turkey?
I got a turkey behind me.
Okay.
Yeah, right there.
Oh, yeah.
So behind me, my drawing there. Try to make this stuff visually attractive behind me in case you're not paying attention. Yeah, A's right answer. A's right answer. It's an alkaline earth metal. The reason I said it because you talked about Thanksgiving. I'm still hungry now. Number 2. So number 1 was A. Number 2, more than 2/3 of elements in the periodic table are what? More 2/3 of elements in the periodic table are what? Yes, Nidal. Yes, Michael. Yes, Alex. 3. No, Santino. No turkey. That's not the right answer. Joseph, yes. Frank, yes. B. Most elements in the periodic table are metals. Most elements in the periodic table are metals. Which element is a member of the halogen family? Where are my halogens? Somewhere there. Which element is a member of halogens? Alex, yes. Tintin, yes. Joe, yes. Joseph? Kai, yes. Choice C, halogens location is group 17. I is in group 17, correct. Number 4, which one's an alkaline earth metal? Have to know where alkaline earth metals are. Earth metals, alkaline earth metals there. Easy once you do that. Alkaline earth metals. Yes, Kai, yes, Ellen, Tintin, yes, Faith. Your alkaline metals. Faith, you check the alkaline metals. Li is a alkaline metal. So alkaline earth has got to be Mg. Question number 5. An atom of which element, so this is a little wordy, an atom of element in period number 2, no, this one's not that bad. Group 14 is in the ground state. What's the total number of valence electrons does this atom have? So location is period 2, group 14. Place sink your battleship, find out which element we're dealing with. Period 2, group 14. Period 2, group 14. Find it, let's see. Period 2, group 14. So period 2, group 14. Group 14. Oh, it matches on up. Which one has the different color? It's got to be C. So we're checking out period 2, group 14. That's the element. Wants to know how many valence electrons does that thing have? Yeah, D. A lot of D's there. Thank you for participating. D is the best answer. Which halogen is a liquid at STP? Which one of these guys is a liquid? There's only 2 liquids on the periodic table. So I don't care if there's more than 2. If there's 2 of them together, it's still going to be liquid. My element is bromine. Halogens, group 17. I would like them to give you a HG there as well. Give you a little curveball. 2 liquids are mercury and bromine. There's no mercury there, so it's got to be bromine. Which elements? Number 7. Which elements contain atoms that form color ions and have more than one positive oxidation state? Thanks, Frank. Yes, Kai. Yes, Greg. Alex, thank you. Greg, you're right. Alex, you're right. Colored ions. These are all Regents questions, guys. These are the types of questions you may see in the Regents, at least in the benchmark for 2. You'll have the same type of questions. We have 2 right answers so far. Colored ions. Colored ions got the transition elements. Colored ions, transition elements. D. Which group contains elements in solid, liquid, and gas phase at room temp? Which group has all 3 phases? So these little symbols here, they don't give you the Roman numerals anymore for these. But just look at the whole number out front. So that 0, that IVB, those don't correspond. They're not going to have questions like that anymore. There's a group 17, 2, 18, or 4. Straight up. Which group has all 3 phases? It's got to be the halogens, group number 17. Choice 8 is the right answer. What more questions we have here? Yeah, maybe we can get through it all. So number 9, which group on the periodic table contains elements that are all gases?
Well, what did you get for 8? You like scrolled.
Sorry. Halogens, group 17. 9, which one has all gases? Which group? Yes, Frank. Frank, thank you. Every one of those answers are right, Frank. All right, group 18, noble gases, inert gases. Choice D. 9's D. Number 10, in which set do the elements exhibit the most similar chemical properties? This one might take a little longer. Which one has most similar chemical properties? Find your elements. Mark them on up. N, O, F. First one. Second one is Hg, Br, Rn, next group is going to be Li. Oh, darn it. They're over here. Next one's all the way over here, way to the left. I'm not going to screw up because I'll mess up my my image here. Al, Si, and P. Al, Si, and P. Similar chemical properties have to be in the same group. These are in the same period. Since they're in the same period, they're going to have the same number of rings. They're not going to have similar chemical properties. Not the right answer. No. These guys are two liquids. They're all over the board. They have different chemical properties. They're not in the same group. A, S, I, P are in the same period, not the same group. Elements in the same group have similar chemical properties. Why? Because the same number of valence electrons. So the best answer should have been, I think these were the choices maybe. They're all in group 1. L-I-N-A-K. Yep, that's the best answer. L-I-N-A-K. Choice C. 2 more questions. Which group contains a metalloid? Which group on the periodic table has a at least one metalloid in it? Group 1, 11, 15, or 18? Yes, Faith. Alex, yeah. All right, cool. So metalloid staircase, you know the location of it. Here's my staircase again. Staircase. Which group has metalloid? That's metalloid, 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 metalloid. Which group has metalloid? Group 15. Good to go. Choice C. 12 is also. Oh. Which element is classified as a noble gas at NDP? STP. Standard temperature, standard pressure. It's okay, Faith. Which one's a noble gas at STP? I'm not giving that answer. That one you gotta do on your own. All right, guys, that's it for today's class. If you have any questions, feel free to ask me any questions you want. I'll be available for the next 15, 20 minutes, whatever you need, to help you with whatever you need. So you can do topic 1, exit pass, topic 2, exit pass as well. We went through 11 questions. The 12th one, I just don't know what the answer is.
What was 11?
Oh, 11 I'll give you. 11 we got C. Number 12, I don't really know. So you got to figure that one out yourself. I'm not giving you the 12th answer. Does anybody want to give everybody the 12th answer? I don't care if you do. 12 is? Whatever. All right, guys, that's it for today. Have a good one. Faith gave it to you. That's correct, too. I don't mind doing this stuff if I have time. Go through that stuff together. All right, have a good day. Make your decisions. Enjoy making a snowman.
12 is neon.
Is it neon? All right, maybe. I don't know. We'll see you guys later. Have a good one.
Bye. Have a good day.
You too. See you later.